In addition to using Hess's law and the standard enthalpies of formation that we did in the last lesson, we can use bond enthalpies in order to calculate the change in enthalpy that occurs in a reaction. Let's really quickly talk about what exactly a bond enthalpy is, though. Bond enthalpy is the enthalpy change for the breaking of a particular bond in 1 mole of a gaseous substance. So this here shows the bond enthalpy of chlorine. If you notice, to represent the bond enthalpy, you put a capital D and then in parentheses the specific bond that you are breaking. Keep in mind that energy must be put in order to break that bond. So all bond enthalpies are positive because you require energy to break bonds. In contrast, when bonds are formed, energy is released. Now, the stronger the bonds you have, the larger the bond enthalpy will be. Since breaking bonds requires energy, that process is endothermic, while making bonds, since it releases energy, it is exothermic. So when we're using the bond enthalpies in order to determine the enthalpy for the entire reaction, we have to keep 2 things in mind. The first is that we must supply enough energy to break the bonds that are not present in the products. The second thing is that you have to form the bonds that are present in the products but not in the reactants. And so let's actually look at an example to make sure we understand this. If you look at this example here, you can see that the first bond between H and C, that does not exist in the products, therefore that must be broken. In addition, the Cl-Cl bond does not exist in the product, so that must be broken. You can also see that the Cl-C bond in the products did not exist in the reactants, therefore that must be formed, and the HCl bond did not exist in reactants, so that must be formed. So this diagram actually shows you what's happening. The first thing that must happen is that the CH bond and the Cl-Cl bond must be broken, and so that requires energy, and therefore the change in enthalpy is going to be positive. In contrast, you then need to form the CCl and the HCl bonds, and therefore that is going to release energy. What you should notice is that the enthalpy difference between the reactants and the products, the reactants have a higher enthalpy than the products, and therefore the change in enthalpy is going to be negative, meaning that the entire reaction is going to be an exothermic process. The way that we actually calculate the change in enthalpy for a reaction is we sum up all of the bond enthalpies that must be broken, and then from that we subtract the sum of all the bond enthalpies that must be formed. So let's actually look at an example to see this in action. Here is a table for all of your average bond enthalpies. But let's do a practice. First, what we need to do is we need to sketch the molecules, because we won't necessarily know all of the bonds that are broken unless we can actually see the molecules that are interacting in this example. So here I am giving you the Haber cycle, which is nitrogen reacting with hydrogen to produce ammonia. And here is the diagram that I found that represents this reaction. Now, keep in mind, one thing that you have to be careful with, nitrogen here is not actually a single bond, it's a triple bond that's being broken. And so what I need to do first is I need to sum up all the bond enthalpies for the bonds that are being broken. So your nitrogen bond is going to be broken. Keep in mind it's a triple bond. So the energy, the bond enthalpy that is going to be involved with this, the bond enthalpy that is required, is 941 kilojoules per mole. I then have 3 hydrogen bonds that have to be broken, which requires 436 kilojoules for each of them, so 436 times 3. So I sum up all of those, and then from that I subtract, well, I have 1, 2, 3, 4, 5, 6 nitrogen-hydrogen bonds that are being formed. Now, the bond enthalpy for the nitrogen-hydrogen bond is 391. So from the bond enthalpies that are being broken, I have to subtract 6 times 391, which is the bond enthalpies that are being formed. And so you can see that right there. I've got my bond enthalpy for my nitrogen, which is triple bonded, plus the 3 hydrogen bonds, minus the 6 nitrogen-hydrogen bonds that have to be formed. And what I end up getting when I do that math, I end up getting negative 97 kilojoules. One thing for you to notice, I had stated that the stronger the bond, the higher the bond enthalpy. Notice that a single nitrogen-nitrogen bond requires 163 kilojoules per mole to break the bond, while a double bonded nitrogen-nitrogen bond requires 418, while a triple bonded requires 941. So it's very clear that the stronger the bond and the more bonds you have, so single, double versus triple, the greater the amount of energy required to break that bond.